I guess I'll repeat what I just said. Binders. If you haven't turned them in yet, then try to do it tomorrow. Or Thursday, as long as not too many people turn it in on Thursday. I should be able to get them all back by Friday. Okay, and then the exams, I'll get those done when I can. All right, so last time we started some new problems. We've talked about pushing and pulling contact forces. We haven't talked about friction or spring forces yet. Does anybody have any homework questions from last time? So I think you did a few pushing problems and a few pulling problems. I don't remember how many I assigned. 1 through 8. Okay, so somebody has a question on one of those 8. That much I guarantee. Okay, yes.
Number 6.
Yeah, for sure. Do you have it with you? Yeah. So this is particle kinetics. Number 6. Could someone hand that up to me? Yeah. All right, so there's an object with a mass of 0.2 kilograms, and it's moving around a circular path. Here's where the object is at the instant that we care about it. The circle's center moves with an acceleration, so I'll call this c. And the acceleration of c is 6 negative 2. The object has a clockwise angular velocity of 8 radians per second. It says it's uniform circular motion, and also it doesn't give you an angular acceleration. Uniform circular motion means constant angular velocity, or in other words, constant speed of the object as it goes around the circle. And the radius is 0.4 meters. So we want to calculate the acceleration vector of the object at the instant shown, and then the net force. So I'll call this object P for particle, and we want to calculate the acceleration of P, and then we want to calculate the net force acting on that particle P. All right, well, the acceleration of P, and if it doesn't say anything about what that's relative to, we're going to assume that that's relative to the ground, is equal to the acceleration of P relative to the center plus the acceleration of the center relative to the ground. This is what's given. So that's the 6 negative 2. And the acceleration of the object relative to the center, that's where we use the circular motion. That's sort of like the circular motion is happening and we're assuming that that C is fixed. You can think about it that way. And so here's the circle. It's going clockwise. And so the velocity vector of that point, if the center was fixed, is, this is the velocity vector direction. So first I'm just going to draw the directions and then we'll calculate the magnitudes. Is it speeding up or slowing down? Neither, so there's no tangential, so I'll just leave that off. Centripetal goes toward the center. And since there's no tangential, this is also the total acceleration. This problem doesn't ask us for the velocity vector, so there's no reason to calculate that. But the magnitude of the centripetal acceleration is omega squared times the radius. So that's 8 squared times the radius of 0.4. So 64 times 0.4, what's the number there? 25.6, and that's meters per second squared. And now it depends what coordinate system you're using. There's no reason to use anything funny here though, so I'll just use this one. So that means that the centripetal acceleration is in the negative y direction. And so that's 0, negative 25.6 meters per second squared. And since there's no tangential, that's also the total acceleration. So that's the answer for part A. No, it's not. No, it's not, because exactly what I started with here. That's what we calculated there was the acceleration of P, assuming that C was fixed. Okay, so that's what we're doing here. And now we have to use relative motion. So the acceleration of P relative to the ground is equal to, this acceleration is the acceleration of P relative to the center. So this, excuse me, is equal to 0, negative 25.6, plus the acceleration of the center relative to the ground. That is the 6, negative 2. And so the acceleration of P relative to the ground is 6, negative 27.6 meters per second squared. Then B, the net force acting on it, is the mass of the object times its acceleration, 6, negative 27.6. And so that is 1.2, and then 55.2, 5.52 negative, and that's in newtons. Any questions about that one? So the reason, so the short answer for like, why did I have to use relative motion is because to use Newton's second law, we basically always want to use the ground coordinate system. What is it about the ground coordinate system that makes it relevant for Newton's second law when the acceleration relative to the center wasn't relevant? It has to do with the fact, so we need to use Newton's second law for accelerations measured in an inertial coordinate system. And that means that the origin is not accelerating and the axes are not rotating. What would have been the problem? So if I had used, so imagine that I had used Newton's second law with this acceleration of p measured relative to the center. What's the problem with that? Why doesn't that work with Newton's second law?
Because the center is accelerating.
Yeah, the center is accelerating. We know that because we're told that in the problem. Okay. And so if the origin, the thing that you're measuring relative to is accelerating, then you're going to have to use relative motion to express it in a coordinate system that's not accelerating. Who has another question about that? Anybody? Somebody blurt out a question about that. Okay. I mean, that's a sort of a subtle, kind of tricky thing that I think is going to come up to you at different times, different problems. You know, it's just going to come up sometimes. So I'll try to clear it up as well as I can when it comes up. But please, you know, when that's an issue, try to come up with a wording for a question about it, because clearing it up in one problem is going to help clear it up in a lot of future problems, you know. Okay, so that was number 6. Any other problems anyone wants to see? Okay. Oh, I don't have that one. Thanks. Okay, so a motorcycle makes a loop-de-loop on a circular path with a radius of 2 meters. At the top of the circle, the speed isn't changing. Okay, so here's the motorcycle. Presumably there's a person on this motorcycle, but that would just make it harder to draw. So, okay, so there it is, and it's going this way. And by the way, since we're just doing an analysis of this one point at the top of the loop-de-loop, it doesn't matter what the shape is away from there. Okay, so like the way I drew it, I mean, even if I had drawn it more carefully, down here it looks like it's not a perfectly circular shape. That doesn't matter. All that matters is that it's perfectly circular right up at the top. And even if it's not perfectly circular, but it can be approximated okay by a circle at that point, we'll get results that approximate it pretty well. The radius is 2 meters. That seems like a pretty small radius for one of these things, but I don't know. They do this thing at the circle. I mean, at the circus, and it is a circle. So that thing that they cruise around, is the height smaller than 4 meters or bigger than 4 meters? 4 meters is like 12 feet, 11 feet, something like that.
I mean, that looks like a kind of a midget height.
Yeah. So I don't know. Maybe this is reasonable. This radius is 2 meters. At the top, the speed isn't changing. And the speed is 15 meters per second. That's really fast. The motorcycle and rider together have a mass of 350 kilograms. That seems really big. Okay, so sketch the system. I already did that. What's the total acceleration of the motorcycle at this instant? So we want to calculate. Okay, so we want to calculate the total acceleration, and then we want to calculate, oh, two more things. The net force acting on the motorcycle. And then third, we want to calculate the force vector that's applied to the wheels by the, what did I call it, the path at this instant. Okay, so first thing we want to calculate is the acceleration. So here's our circular path. The object is moving this way, and the magnitude of that velocity is 15 meters per second. I'm going to do my coordinate system in the usual directions. Since it's not changing speed at this instant, there's no tangential acceleration. There is a centripetal acceleration. And since there's no tangential, that's also the total acceleration. So the magnitude of the centripetal acceleration is omega squared r. We don't have omega. We could calculate it from v, but remember this is also equal to the speed squared divided by r. So the speed squared is 15 squared. R is 2. And so this is 112.5. That's a big acceleration. You know, 10 Gs, 11 Gs, that's a lot. If that answer isn't, well, let me first give the vector, but so the centripetal acceleration, we know that that's in the negative y direction, so the acceleration is 0, negative 112.5 meters per second squared, and that's the total acceleration. If that isn't realistic, I mean, there's two things. That's a really big speed, you know, over 30 miles an hour going over the top of a thing that only has a radius of 2 meters. So, you know, probably the radius is a little too small. The speed is a little too big to be realistic. And by the way, this thing is going to be going faster when it gets to the bottom. So the acceleration at the bottom is going to be even bigger. Okay, so now we have that acceleration. Next, we have to figure out the net force acting on this. The net force is the mass times the acceleration vector, so that's 350 times that acceleration vector. Can someone multiply those for me? So 350 times 112.5. 39,375 newtons. Okay, so that's the force that, well, that's the total force. And now what we're going to do in part C is break up that total force, that net force, into a part that's, into all the individual things that apply those forces. So we're going to have to start with a free body diagram and figure out what the individual contributors are. Negative, yeah. Yep. Okay, so for part C, so now I'm going to do a free body diagram of the motorcycle and the rider. That's upside down. Okay, so what forces are acting? There's a weight force coming from the center of mass. So that's 350 times 9.81. And now go around the boundary of what we're isolating, looking for contact. Where do the surroundings make contact with the boundary? Yep, only at the wheels. And you could do this as two separate forces, one at each wheel. For now, since we're doing particles, you can always just treat it as a single force. I'll call that N for normal force. Okay, so what we have is two forces pointing down that have to equal that total force of 39,750. So Newton's second law says 0, negative N plus this weight force. What's 350 times 9.81? So 0, negative like 34, 3,400, what? And these have to equal the mass times the acceleration. The x equation doesn't give us anything useful. That just says 0 equals 0. But the y equation says negative N minus 3433.5 is equal to negative 39,375. And so N is equal to 39,375 minus 3433.5. So what do you get for N? 35, 931? 941.5. So that's the magnitude of that force, that pushing force that the path has to apply to the wheels. The problem asks for the force vector. Well, this is the force vector that we're looking for. This is the force vector that's applied to the wheels by the ground. We just didn't know what the value of N was yet. So now you can take that value of N, plug it back into that vector, and what you get is the force on the wheels by the ground is equal to, so we already knew it was 0, negative N. And so plug this in for N and you get 0, negative 35,941.5. which is probably a lot higher than is really required because we probably have too big a mass for the motorcycle and the rider. Plus, we probably have too small a radius. Plus, we also probably have too big a speed. But this is exactly the kind of calculation that people are doing when they try to choose the thicknesses of the steel that they make that cage out of or whatever that the person is riding around. Okay, so once you figure out what kind of force that path needs to apply to the wheels, then you can start to back calculate, okay, not using the stuff that we've done, but using the kind of ideas that you'll talk about in statics and deform later on. Like, okay, how thick do these, so say we're going to use steel that's shaped into circular tubes. How thick do the walls have to be? How big around do the walls have to be in order that a force like that isn't going to break anything, you know? So this kind of calculation is pretty relevant for engineering applications. By the way, we could use this exact same approach to figure out what's the slowest speed that we could have at the top and not have that motorcycle fall off the path, basically lose its contact with the ground. Do you have any idea like how we would go about doing that if the question was so? What if we wanted to know the slowest speed at the top so the motorcycle would maintain contact with the ground? Okay, any ideas about how we're going to do this? What's going to be our, so basically we have to plug in a value somewhere in these equations that sort of defines the cutoff between this having contact with the ground and losing contact with the ground. What are we going to plug in as our criterion for maintaining contact with the ground? Exactly. And we might as well just say 0. But so what we're going to do is we're going to say, okay, it's still in a circular motion, okay? But we know that the path can't pull up on the wheel, okay? So we're going to do this problem assuming that normal force N is 0. And we're going to calculate what the slowest speed is, or basically we're going to calculate what the speed is so that normal force is equal to 0, but it still stays in circular motion, okay? All right, so let's do this again. So again, we have this free body diagram. And there's a weight force of 350 times 9.81. And then there's this contact force N. And our circular motion, I'm sort of redoing a lot of this analysis, but we're going to assume that speed is constant up there. So we're going to assume that there's a velocity vector this way. And it has a magnitude capital V. And there's a centripetal acceleration this way. Well, what do we know about the magnitude of that centripetal acceleration? That's equal to omega squared r, which we can also think of as v squared over r. This time we're going to leave that v as something to calculate, but the r we still know is 2, so this is v squared over 2. The centripetal acceleration is in the negative y direction, so the centripetal acceleration vector is 0, negative, I guess I'm just rewriting this as negative 0.5 v squared. And that's the total acceleration. Okay, so now, depending on what the speed is, that's going to change the magnitude of the acceleration, but we have the acceleration expressed, in terms of that speed. That's what we want, because now we're going to be able to calculate what v is so that it meets our criterion. And the criterion we're going to use is that this normal force is equal to 0. So now when we go to Newton's second law, we have the weight force, 0. Where was that? Negative 3433.5. So 0, negative 3433.5. And then we have that other force, 0, negative n. But we're setting this equal to 0 to define the exact boundary between contact and no contact. And these have to be equal to the mass times the acceleration. The x equation doesn't give us anything, but the y equation says negative 3433.5 is equal to negative 175 v squared. And so v is equal to plus or minus 3433.5 divided by 175, and then take the square root. And what do you get for v? 4.43, so about 10 miles per hour. Meters per second. So if you've ever wondered how fast you'd have to throw your Hot Wheels car to get it to make the loop-de-loop, you can do this calculation. This way of thinking about it should always work. Or to ride your bike around a loop-de-loop. That'd be rad. Yes?
Can some people run that fast? Wouldn't that mean you can run around it?
Well, that's only for this specific one. And they can run 10 miles per hour, but I think the catch is they couldn't still be running 10 miles per hour once they've run to 4 meters up. So that's the issue, because that's not saying that. So that's not saying that if you get your Hot Wheels car going 4.43 meters per second here, it's going to make it around the loop. it's saying you have to get it going fast enough down here that after it's slowed down all the way going up, that it's still going 4.43 up there. Any other questions about that one? I like that question because I think for more than half the people in the class, you've asked yourself that question at some time or other. Maybe not since you've been 6, but that's the answer. Any other homework questions you want to see? Three. Okay. Oh, you got thrown off the elevator? Yeah. Oh, yeah. That's horrible.
How do you get someone off the elevator?
I'm not riding that elevator. Okay, so you have a 10-kilogram cart that sits on an elevator. And the elevator accelerates down at 1 meter per second squared. What's the force applied to the cart by the floor? Well, so sometimes these elevator problems are a pain because you have to think about relative motion and all that stuff. This one, actually, you don't really have to think about relative motion. You could do it that way. But the reason you don't is because if you imagine what's going to happen here, this is going to stay on the floor of the elevator, you know? And so you don't have to worry. It's not like this is moving relative to the elevator and then the elevator's doing something else. Basically, if you set it up as a relative motion problem, here's what you would have. The acceleration of the cart relative to the ground is equal to the acceleration of the cart relative to the elevator plus acceleration of the elevator relative to the ground. And one of those terms would go away because this cart is not accelerating relative to the elevator. You can think of it as all kind of mounted together. Okay. So then so we'll start with a free body diagram. We have a weight force of 10 times 9.81. And the only other force, the only place where the surroundings make contact with the boundary is at the wheels, so I'll call that N. And then Newton's second law says, so 0, this weight force comes out to be negative 98.1. Plus 0n is equal to the mass of the thing we isolated times the acceleration of the thing we isolated, which, like I said, is simple in this problem. It's just using the -1 from the problem. And so we have an x equation that says 0 equals 0. That doesn't give us anything. The y equation says negative 98.1 plus n is equal to -10. And so N is equal to 88.1 newtons. Okay, so I want to say a couple of things about this. The first one is that an elevator is not always accelerating. So this isn't true whenever the elevator is going down. What an elevator does is it accelerates a little bit. So as it starts to go down, it accelerates a little bit up until it gets up to the speed that it wants to be at. And from then on, it's a constant velocity. So you would only have this effect for that short part at the beginning, right when it goes from at rest to getting up to its speed. Okay, well, everybody with me on that? Okay, but the second thing is that's kind of interesting is notice that this contact force is exactly what a scale, like a bathroom scale, does to your feet. Okay, and so what we're really doing is, like, another way of thinking about what we're doing here is measuring what a bathroom scale would think the weight of this object was. And so as this thing is accelerating down, the bathroom scale reads, I mean, the weight of this object is 98.1 newtons. But while it's accelerating down, in this case, the bathroom scale reads a smaller weight. And if it was accelerating up, the bathroom scale would read a bigger weight. So if you ever want to lose weight or gain weight, you know, you can just bring your scale on an elevator. But you have to look away quick, because if you'll look, you'll be happy. And then if you keep looking too long, the speed it'll get to a constant speed, constant velocity. There's no acceleration, and you go back to reality.
Or you can just go to the moon. That helps.
Yes, the moon you could, yeah, but you got to wear a heavy suit. Any questions about that? Okay, let's stop there, and tomorrow we'll get to some new material. Yeah. You pass this back. Great, thank you. Yes, if you have your binders and your